Hello, my name is Behrang Fouladi, and I'm a security researcher working for SensePost. This work is part of the research, my master thesis, and it's about reverse engineering the software part of the smart cards in order to find the vulnerabilities or possible backdoors. I hope you enjoy it. First, let's see what is a smart card and what makes it different from the magnetic cards. You probably have lots of them. First of all, they embed a microchip inside that plastic body. And the second important property of these cards is the tamper resistance of the chip. So it means that the chip is designed in such a way to resist different type of the invasive or non-invasive attacks. You might have heard about attacks like power analysis attacks, which is, in simple terms, is trying to infer or extract data out of that chip based on the power consumption of the microprocessor. Or invasive attacks, which actually involves opening the package of the chip in order to insert probes, change the circuit in order to patch the algorithm, or even read the gates and reverse and find out what is the protocol or algorithm running on the card. So the tamper-resistant property of this card made it a very ideal solution for applications like telecommunication, when the operator wants to bind your identity subscription to the handset, or for banking applications when there's a need to store your keys or certificates in a very secure and small token. Here's a sample of one of those chips. This chip actually comes out of this .NET smart card. So how many of you had Commodore 64 or Spectrum? Yeah. So that thing, if you compare the size, it has like a 80 kilobyte RAM, 400 kilobyte EEPROM, and is also includes a 32-bit microprocessor along with a crypto processor. So it is much more powerful than a Commodore you had, but in that size. Add to this, there's also one important property is the tamper resistance of these chips. So there are primarily two main categories of these smart cards. The first one is the single application smart cards. One of the very famous ones is this Oyster card, transport card. Most of you have used so far, which actually is an offline card. What it stores is a counter, which whenever you top up the card, the counter increases. It doesn't connect it to any backend, and the card is completely offline. At the end of the day, there's a bulk FTP download to London Transport's back office. But the card itself is an offline solution because you need a fast transaction. At the gate, there are lots of people. They should pass the gate quickly. So there is no time for online transaction. So this tamper resistance property of this card actually protects that counter. The other type of the cards, are the single application cards, are these pay TV cards you use. And the main purpose is to protect that private key assigned or sold to you, and the algorithm, the key derivation algorithm, which generates a new key every seconds or maybe less. And finally, the access control cards, which Most of these cards used to have proprietary algorithms in terms of authentication or in terms of communication with the reader. But it has been changing right now, and they are using more open platforms and known algorithms. And the other category is the multi-application smart cards, which, as the name implies, is capable of storing and executing different applications. Could be access control applications, physical access control. Could be the identification. It can store your biometric data, fingerprints, an image, or logical access control, access to the workstations, or remote access through a VPN. Cashless payment in big companies, for instance, they provide the employees or personnel with a prepared card they can use in cafeteria or restaurants, and car parking. So all are running on the same chip and protected by the security features of the operating system of the card to actually isolate the high security applications from lower security ones. How many of you have orange SIM cards? Okay. So what applications do you think are running on that SIM card? Any idea? Yeah, just one of them is obviously is the GSM authentication and session key generation application, and other important one is the SIM card management applet, which is used by the operator to remotely install stuff on your SIM card or update stuff on your SIM card, disable or enable application. Are there any other?
Address book? No address book.
Nice. It is actually not an application. It is part of the data stored on the file system. So it is actually a file, not an application. But is managed by the card management applet. So any other applications might work. So we don't really know what is running on this. However, we can sometimes find out by checking the traffic between the SIM card and the handset. So one of these, especially on the orange SIM cards, is the SIM tracker applet. So the idea of this applet is that whenever you change your handset, insert your SIM card in a new handset, which has a different identification number, IMEI number, the applet captures that number with the cell and location information of your phone and send it back to the orange without your knowledge. So this is one of the samples of the applications that can be executed on your smart cards without you even realizing it. And the purpose for that is mainly for police investigation and stuff. There has been some incident reported related to smart cards, both protocols and softwares of the smart card. The famous one was the cloning attack against these Oyster cards, where they were using the NXP Mayfair cards at that time. And the problem was that, again, the NXP implemented a stream cipher, proprietary stream cipher algorithm, which was found to be weak against key recovery attacks. And in a couple of seconds, you actually could extract the card's private key and copy it on a new key. The other one was the research released by Cambridge University. It was the attack against the banking cards, against the EMV protocol. And but this one also need some kind of, the attacker need physical access to the POS terminal. The most recent one was a malware attack. The Psychopod malware targeted the Pentagon smart cards. It the attack was running for 3 years, since 2007, and just only discovered in 2011. And it is interesting because at the same time, summer 2011, we were doing an investigation, break-in investigation for a defense equipment manufacturer, and the malware used in this case for that psychopod, the sample of the malware, had exact same set of command and control instruction as the malware we found on that different client in a different continent. So it shows that these kind of attacks, because they can be very covert, very difficult to detect, and you see a trend starting from algorithm, targeting the algorithm, targeting the hardware, and know the software. So why it is important, in my view, to care about the malicious software on the smart cards? Because so far, most of the industry people, smart card industry people, might argue that, well, these are trusted applications running on the smart card. Mostly the issuer writes the application, deploys it in here, and there are no cases that we use outsider developers and so on. The problem is that by 2014 there would be 8 billion smart cards in the market, excluding the RFID tags. This is just the smart cards. It has a large distribution. The other thing is that we are fastly moving into the concept of this Internet of Things, which is the idea of embedding chips, tags on this stuff we interact with it or carry. And those chips, the best solution and the secure solution for them is the smart cards chips. So again, these kind of things these kind of chips will be embedded in most of the devices you might ever not notice. Your refrigerator, your power meter. The third one is the chip-enabled payments, especially the NFC market right now. The last month, the first NFC SIM cards were rolled out in France by Orange. And the problem and the interesting thing with these smart cards is that so far the applications were mostly developed by the telecom, by the issuer. But right now for the NFC applications, you have to deploy third-party applications on that SIM card. And there is like some company wants to issue, you're selling handsets, and you have a partner company wants to give the users a prepared card together with that handset. So you have to deploy that company's application on your SIM card, which could be malicious, and you don't know what is going on that application. The other thing is the hardware backdoors. It has been an interesting topic in the recent years on embedded system, and especially on these tamper-resistant stuff. That is very difficult to extract the code, disassemble, or read to find the deliberate weaknesses or hidden codes. And finally, the cyber war is going on right now. You have seen high-profile attacks so far. Malware that is deployed in underground facilities which are not connected to the internet. So the same can happen for these kind of secure devices. So in response to those threats, the smart cards has a very important security defense called smart card firewall. It's not about the firewall we know, like network firewall. It's more a concept of isolating different applications on the smart card. So you can see there are 3 different applications running on top of a virtual machine. Normally, these cards today have Java.NET virtual machine, implementation of Microsoft.NET. Even I have seen recently implementation of Google Dalvik virtual machine on the smart cards. So the important security feature is the application firewall, and if something goes wrong in that place, then it is possible for applications to access their data. So the .NET Smart Card, which was my research interest, was the first .NET virtual machine implementation on a chip, long before the even Microsoft .NET Micro Edition, which was released in 2009. This thing was produced in 2004. It has native support in Windows Server 2008 and Windows 7. It means that the driver is already installed there. It is used mostly as a corporate badge. Microsoft itself, the employee badge of Microsoft is of this type. And so far, 300,000 cards are delivered to Microsoft based on the vendor's website. And finally, this card is also used by MOD and DOD. In the case of MOD, they use it in Microsoft networks for some frontline applications, remote access to those applications. And in case of US, this is not the only card they use. It's a combination of Java card, one-time pin generator. Here's an overview of that smart cards file system. You see it is very similar to DOS file system. The drive names, virtual drive names, the executable names, the executable are exe. The library names, again, DLL files. And here is the actual .NET libraries. You can see it just consists of two DLL files, MS Core Lib DLL, which implements all the base classes of .NET, and the Smart Card.dll, which implements the classes like PIM management, transaction management, communication for on-card application. They can be used by on-card applications. The security model of this card is simple yet effective. As you can see, every application on the card is signed by a RSA key pair, and the different applications then can be identified based on their signing entity. The virtual machine also can ensure the integrity of the code using those signature, as well as the data origin, because you can verify the signer and decide, okay, I'm not going to execute, I'm just going to execute these kind of programs signed by this vendor. The applications can create files. As you can see, the application B can create files on the file system, or they can call APIs from DLL files, if provided that they are on the same application domain, means that they are signed by the same vendor. However, the card does not use the 128-bit public key as an identifier. It uses another concept named public key token, which is a shortened format of that RSA public key. It is 8 byte long. As you can see, there is an application password valid on my smart card, and the public key token for that 8 byte is visible there. So the card security is based on that identifier. As you can see, that library, card module interface, has an access list which allows that particular public key token to execute it. So no other application would be able to make API calls to that DLL. This is the code security principle of this card. And the data security. Data files on the file system, as you can see, that store that file. That file is only accessible to to applications signed by that public key token, 26, 27, and so on. A little bit about the development, application development of this card. Here is Bob. He's a .NET application developer, but has no experience with smart card development. And he has been asked to develop a smart card program. So he has two main challenges. First, how to deploy and debug his code on that smart card, because he can't obviously simply upload his .NET assembly file to a smart card. And the other challenge is how to communicate with that application on the card. The communication protocol between the smart card and the reader is APDU, Application Protocol Data Units. It's a standard protocol, and Bob needs to learn it if he wants to call the application, send commands, and get responses. However, this specific card makes life easier for him. So he first compiles his application into .NET assemblies, the regular PE file, Windows PE executable. Then the vendor has provided a converter program, which allows him to automatically convert that .NET assembly to a smart card binary format, and also sign it, and then deploy it on the card without knowing the details of that format, card binary format, or even know how to sign the binary. After deploying the application, it is time to use the application. So here, he can simply use .NET remoting technology to call the application. The .NET remoting technology, as you may know, allows to call services, remote services, .NET services, over different protocols like HTTP, TCP. So in fact, he can make HTTP calls to a smart card. But in fact, there is a communication proxy component, again developed by the vendor, to translate those .NET remoting calls into the APDU commands. And these two components forms the vendor's SDK, Software Development Kit, which was the main area of my research, to actually reverse it and to get information about the virtual machine or possible vulnerabilities. Okay, how secure is .NET card? The chip inside this card is an Infineon chip. It's a German semiconductor producer specialized in smart card chips, and it has EAL 5 certification. So EAL mostly, as you may know, is evaluation assurance level, which is a numeric grade of evaluating the IT product, security of IT product, from 1 to 7, and is widely used by smart card vendors to give an assurance to their customers that, well, our product achieve this level of security and you should be fine. This was for the chip. The operating system on the chip is designed to achieve EAL 4, which is a level more than EAL 4. The plus implies that it also contains some of the tests from EAL 5. The EAL 4 audit, normally, just to give you an idea how it works, it is performed by certified bodies and certified companies in each country, and takes 6 or 9 months, costs between high 10Ks to low 100,000 K pounds. And it includes independent penetration testing, and in some cases, the source code review of the operating system. So it should be pretty much secure. And no published vulnerabilities so far. I haven't seen any vulnerabilities reported in this card. Normally, smart card industry is a secretive industry. And if researchers find something, mostly academic researchers, they just publish a paper. They have their publication. The vendor has free assessment, and everybody is fine, but not the consumer. So, a little bit about the reverse engineering of embedded systems. Currently, we have very good tools, even procedures, to reverse engineer the embedded systems. Mostly Linux systems, embedded systems based on Linux operating system. There are even firmware modification tools out there. There are disassembly tools. And the interesting thing is that most of these embedded devices have some kind of debugging feature, either in the form of a JTAG port or a serial port. However, this is not the case for smart cards. In the smart card case, we don't have access simply to any kind of firmware. There is no operating system chip for obvious security reasons. The traditional tools, the debuggers, disassemblers, IDA Pro, OLEDBG, whatever, are useless. And the vendors, for obvious reasons, do not release testing tools. There's only an emulator tool available for Java cards, but it's just a reference implementation, not exact actual implementation on a chip. And the most important thing is that these chips are designed to be resistant against hardware attacks. So they have sensors, lots of sensors. This is the chip. If you wash this PVC with acetone, you can get the chip. So you see it is a black chip, and certainly it has light sensors because of this color. Light sensors, sometimes even sound sensors, shields to protect insertion of probes or reading the circuits, and encryption. The code, actual firmware code inside the chip is encrypted. If you even manage to open the circuit, get to the circuit, the gates are obfuscated. You again need to find out the encryption or obfuscation method used by that vendor. And the other important thing is that most of today's smart cards has on-card bytecode verifiers. It means that the application you upload onto the card, the .NET application, the Java application, is first verified to comply with the language specification by the virtual machine. And if something was wrong, it will reject execution of the code. However, I decided to develop the first tool, which allows you to visualize those smart card binaries, modify them, and redeploy them into the card for security research purposes. So the Hive Mod allows you to see different sections of the binary, different headers, different metadata tables, manipulate any of those bytes easily, quickly, and reassign those modified test cases, upload it into the card, and then probably you will kill the card in some cases, or you will find vulnerabilities. So let's go into the details of this card binary before we actually try to test the vulnerability on this card. Through the reverse engineering of that SDK and converter program, I managed to find out the file format and actually wrote that the software tool. So the file format consists of 3 fixed size headers: compiler header, digital signature header, counter header, 7 metadata tables, and only after these sections is the program code, actual program code, which is in MSIL opcode format, which is noun format. And finally, a signature is calculated on all over these sections and appended to the end of file. Obviously, then the VM would be able to compute the same signature again on the card, compare it with the signature appended, and ensure that the file is not modified. I found out that only 4 of those tables are in common with Microsoft.NET P format. Not even very similar, just the names are the same. The fields inside those tables are very different. So as a result, you can't use tools like the Reflector, like .NET patchers for this purpose, for testing .NET cards. Okay, so before attempting to manipulate or fuzz this format, we have to think about the interesting sections of that format. As you can see, that digital signature header could be interesting because the security model of the card is based on the digital signatures. If we change values there, we might be able to do some interesting stuff. And obviously the other thing is the program code, because this is the section parsed and executed by the virtual machine. So let's take a look at this header in details. And here is the members of that digital signature header. As you can see, there are 2 fields, RSA public exponent and RSA modulus. You may know that a RSA public key consists of just these 2 values. There's a public key, there's a public exponent and modulus. So it defines the public key of the assembly. And there's another interesting thing. Here you can see that the public key token, which I mentioned earlier, is again embedded in this header. So the question was that why there are 2 related values and repeated? Because the point is that I found out the public key token value can be easily calculated using this simple formula. And it just depends on the RSA modulus, right? So if you have the RSA modulus there's no need to have another field for public key token. So it arises a question mark. Any attack ideas? Do you think it can be used for any? Suppose that yeah?
So do you have the same kind of collisions as you have when you talk about PGP fingerprints and often specified with the last 8 bytes? Yeah, something similar to that, but how we can take benefit of that? So you create another application that has the same loss, and then put that on, and then it's shared UID, this essentially means that you can access the
Excellent. So it is actually an old school attack. It's when you test a web application, you normally, in order to test the authorization controls, you normally change the username or change the credit card number in order to try to access another customer's data. So here we are going to change the public key token to the public key token of another application in order to access its data. So let's use this tool to test for this vulnerability. I prepared a video, but if you're keen to see it in real, I have the reader and the card, but because of the time constraints, I just have to show the video. Okay, so here is a simple application I developed. It's a password manager application which stores your site credential on a smart card, and it is protected by a PIN card. As you can see, for instance, my Yahoo site username and password is stored here. If you lose the card, you shouldn't be worried because it would be blocked in 3 PIN retries. So even if the hands of an attacker, your passwords are safe using this smart card. So here I'm going to add an account, and you can see my account right now on the smart card. And here is the username and password. Okay, let's take a look at the card, inside the card, how it looks like. This is the Card Explorer program, part of the SDK, allows you to manage the file and deploy the application. You can see the password wallet program there, executable. Let's see its signature value. You see public key token, it has a public key token starting by 26, 27. And it has a file, storage file, which has an access list set up for that specific public key token. It means that only the assemblies with that public key token can read and write that file, which are the actual storage of username and password. There's a malicious program there, grab the wallet, and it has a different public key token, starting by 65, C3, blah, blah. And obviously, it shouldn't be able to access the file. Let's run it. And you get the attempt to perform an unauthorized operation. As you can see, the grabber service, grab file, when it attempted to grab the file, it failed. Let's modify that using the Hive Mod. This is the Hive Mod program. I just load that malicious program again into Hive Mod. And here's the signature header. And inside the signature, there is a public key token, right? So just to check that it is the same public key token you see on the card to ensure that it's the same. Okay, as you can see, 65, 65, it's the same, okay? Let's reset it to the public key token of the password wallet and see what happens. Just simply replace the 8 bytes with that value easily. And in order to spoof the identity of that application, of your password wallet. And verify the signature. Obviously, the signature is not valid anymore because we have changed the file. We are going to resign the file with OR key. We don't know the password valid key. We choose OR key. And this is the signed application. Here is the signature appended to the end of the file. And we're going to save it into a temporary file, dummy.exe. And going to upload that dummy.exe into the card. Just rename it to grab the wallet and open the Card Explorer to upload the file. And The point is that if the card was not vulnerable, the card should reject the file, because the file is manipulated. It didn't reject the file, and it successfully uploaded into the card. Let's execute it this time and see if it can access the password files right now. The same, you see the same public key token. It has the same public key token right now as the password wallet. The same public key token. So let's run the file grabber again. And this time you can see my passwords there. Password, Behrang, Yahoo password, or what. So this seems like a backdoor to me, not a vulnerability, but no judgment. So, okay. So you see, it is the Hive Mod made the life very easy to test actually pen test the smart cards. So far, I'm not aware of any programs designed for this purpose. So I myself spent 2 months to reverse engineer that SDK. And I also use, during my developing the program, use hex editor for binary patching. And it was frustrating because when you have 2 different .NET applications, because they have obviously different lenses, different sections. And if you want to patch a same section in two files, they are on different offsets. And you have to recalculate the offset each time. But using the visualization of this tool, it is very easy to do so. And the only sacrification you should make is that destroying some cards. So the card is very expensive. Compared to other cards, Java card is just $1 each. This card is 20 euros. So it is common to destroy cards when you test for vulnerabilities. I actually destroyed 10 cards. Okay, so could it be used in real-world attacks? I think so, because imagine a corporate badge with an ePers app and an access control app. So through some method, could be social engineering or very advanced methods like having insider, or advanced methods that governments use to plant stuff. The attacker modifies the public key token of the ePers application to the public key token of the access control app, and deploys it and get it deployed to the card. He might even doesn't have the access to do so. So whenever an employee or personnel will go to the corporate cafeteria, make a payment, the POS terminal, which is again running a client version of that ePers application, and logically should be under the control of the entity managing the corporate cafeterias, because in most big organizations these stuff are outsourced in a military base, in a big corporate. So the POS terminals these days are also mostly remotely managed through GSM network. This is the case for commercial places. So then the attacker can simply exfiltrate the data through the GSM network, or if it was like a military base or very isolated place, no GSM connection, then one of the insiders can go just make a payment. This time the POS application just copies the stored data into his card. He just took the card out. It is not suspicious. It is the same personal card. At least looks like the same personal card, but in fact it is not. Well, you might argue this might be fictional, but this is a document from a vendor's website, MaltOS card, which actually explains project they have done in 2005 for a NATO member military. And the interesting thing is that you see the control access to physical locations, the access control applications, sits on the same card as cashless payment application and the health insurance. So obviously these are different readers and these are different security levels. So if some entity in the level of a government or some agency like that wants to perform such attacks, it's probable. And this is some evidences that these stuff has been used in very sensitive places. So what was the vendor's response to this report? The first response is that, yeah, we acknowledge this, but the attacker needs to know the administration key of the cards to deploy his application. But the point is that if attacker knew the key, then he would simply download the file. Why should he deploy an application? And they say that these keys are normally stored in HSMs. How many of you use two-factor authentication in your company? Just one. Okay. Do you have card management solutions? How they issue the card for you? Do they have any kind of card management solution which helps them to quickly issue a card for you? Okay. And do they use HSM? You don't know. Okay. So I don't think lots of organizations are using the HSM. They simply store those passwords in form of hardware or even a smart card on a different smart card. So I don't think this is a good justification. The other thing is knowledge of public key token of the target application is required. Well, this is a little bit strange hearing from a security vendor because public key is public. You know? I don't know, because public key is public, and then having the public key, you can compute the public key token, right? But this one is sensible. It says that the targeted application must store data on the file system, not inside the code, its code. And this is true. And matter of fact, this is the recommended way. If you develop some applications that have like a 128-bit encryption key, okay, it's like 60 bytes. So it is better to just make a byte array, put it inside your file, inside your application source code, not store it as a different file. There were more vulnerabilities, and I actually find the vulnerability, another vulnerability in array initialization method of the .NET virtual machine, which could be used to partially dump the memory. And this is very interesting on smart cards because different programs load different private keys into their memory space. So if you were able to dump memory, you actually are able to get the keys. But so far, my attempt to read more data resulted in card being destroyed. And here, this is a dead card. And it costs a lot, you know, because the point with these tests is that the chances that the card being destroyed, because the VMware has self-check and health check startup routines. If it detects that something has been changed in the memory route, it just refuses to start. So, well, this is not a threat to your organization unless you are using the smart card, the .NET smart card, to run applications. If you are just using it to store your certificates or just to store your private key or use it to sign your emails, you're probably safe. Otherwise, you should check your applications public key tokens to make sure that no two applications have the same public key tokens. I mean, different vendors having the same public key token. This is alarming. And finally, use a secure card management system. And unfortunately, the thing that is strange with these systems right now, this specific card, the vendor provides a web-based card management system to its customers. And it has some strange features like remotely unblocking your card. Okay? So it means that they have implemented some logic on the client side which can be reversed and possibly used to do funny stuff on these cards. So I would recommend to use a dedicated, not hosted card management system. And the thing about the smart card application operating system, unlike the normal softwares, you can't update them. So right now there are thousands of card vulnerable out there. There's no way to patch them, and you can just reissue the cards. And the thing is that smart card operating system applications and the management softwares need pen tests too. I haven't seen this, such efforts in the industry to actually look at these small but critical elements. The Hive Mod tool is available to smart card vendors or security researchers. Just contact research at SensePost. I also like to thank Dr. Kostas, who was my supervisor for this research. And thank you for listening. Any questions?
So I've got two questions. Firstly, you mentioned that there is a signing process that goes on. So why do you think the signing itself isn't used to identify the applications? Secondly, what CAs do the smart cards actually trust? Because presumably you can't, I mean, Microsoft invalidated a whole bunch of CAs recently. There's presumably no way of updating that list on the card.
Exactly.
For the same reasons
as
the
OS. So signing doesn't provide, as you can see with our test, we could easily resign the modified assembly. We could easily resign or modified assembly and make it look good. Okay. The only use that it has is the origin authentication, the signer's identity. The problem with the smart card is that they don't have that hierarchy like softwares we use. This one has that hierarchy. The Malt OS, and the interesting thing about the Malt OS, because it's a high security card and government and military level, EAL 6. So the chip on this card is Hitachi chip, the most secure chip. Anyway, these guys have set up that CA structure. They don't allow you to freely download the SDK. In order to develop stuff for this card, you have to buy a developer license. It costs $30K USD just for a start. And interesting to know, your biometric passports has that CA structure. And guess where is the CA? Do you know where it is? This is in Singapore. So it's not a very good place. So yeah, that's very important point about there should be a key hierarchy, key management hierarchy if we want to actually deploy more and more applications to these things. Okay, any other questions? Yeah, thank you. Thanks a lot.